Do you remember how I said I really like the fact that when the dart sails through the air, I said it moves from right to left, right? It moves up and down, and it moves backwards and forwards, right? Those three directions represent the three dimensions of any object. We live in a three-dimensional world. We have height, width, and depth, right? 3 dimensions. Okay, now in math, those are often referred to as the axes, the x-axis, the y-axis, and the z-axis. Have you guys heard of this before? Yes. Okay, the 3 axes in three-dimensional space, right? So for this class, we're going to say that the x-axis is the axis of rightward motion and leftward motion. Okay? In fact, so if we drew an x-axis here, this is what it would look like, right? So right on the x-axis, an object can go to the right or it can go to the left, correct? The y-axis will represent upward motion and downward motion, okay? And then the z-axis, which by the way the z-axis isn't, I've never really seen it used much in AP, or at all maybe, in AP Calculus, but we're going to talk about it briefly. Anyway, the z-axis will be forward motion and backward motion. Is that okay? But there's nothing official in AP Calculus that says it has to be like that. I just want to set the stage for how we have our conversations. Go ahead, Brandon.
That way, how do you draw that?
I can't. But I have good news for you. I have very good news for you. Okay? Just hold that thought, and I have very good news for you. Okay? All right, are y'all ready? Okay. The name of what we are learning right now in AP Calculus is called rectilinear motion. Rectilinear motion. Something like that, yes. And the recti in rectilinear is kind of the same as the rect in rectangle. Okay? Rectilinear motion. It's not the other recti.
That was bad.
Yeah. Okay? All right, so rectilinear motion. This is basically what rectilinear motion means. If you want to write something next to it, this is what rectilinear motion means. It basically means one-dimensional motion. One-dimensional motion. And what I mean by that is this, is in this class, in AP Calculus AB, we are only going to deal with one of the 3 axes. We are only going to be dealing with the position of an object, the velocity of an object, and the acceleration of an object as it moves along a single axis. That's it. So it might be moving along 3 axes, but we're only going to follow it along one of those axes. Okay? Most of the time it'll be the x-axis. Sometimes it'll be the y-axis. Okay? Now in AP Calculus BC, in that class, after learning about rectilinear motion, you would learn about parametric equations, which refers to or looks at 2-dimensional motion, motion along the x-axis and the y-axis at the same time. Okay? Yes, sir.
So, what about like when they look at like objects in space? Do they use like that?
Not in AP Calculus, if that's what you mean. Okay, so here's the deal. I don't know if this answers your question, but I'll tell you. So then, when do you look at object in 3-dimensional motion? Calculus 3 is what I understand. So you go to college, take Calc 1 first semester, Calc 2 second semester. Third semester you take Calc 3. Fourth semester you take differential equations. And during Calc 3, that's when you learn. And I've heard that. No, I haven't heard that. I thought I heard Calc 3 was the hardest or the easiest. I can't remember. I think it's the hardest, honestly. I don't know. I haven't taken it. I got a degree in economics. So anyway, Calc 3, I understand, is where you learn about 3-dimensional motion. or velocity on 3 axes, position on 3 axes, that sort of thing. Okay? All right, so are we okay so far, folks? All right, here's what I have to try and get in your head in the next 20 minutes. And I may need the whole 20 minutes to do this, okay? I need you to understand how we go from one-dimensional motion, so just motion back and or right and left along the x-axis, to a function, to a graph. Okay? And I'm not really sure, I can't remember how I did it the other day. I sort of remember how I do it, or how I tend to do it, so we're going to do the best we can here. Okay? All right. Where am I? Okay, so look. I want you to imagine that we arbitrarily select what is called the origin. Okay? That origin is referred to as position 0. So this is a position. The x-axis is the position of the object, where the object is. And the object will be either to the right of the origin or it will be to the left of the origin. Does that make sense? Okay. All right. So, like if we stuck with the origin over there, I am currently, let's say, 12 feet to the right of the origin. Okay, and then I can, anytime I move, I am either moving away from the origin or I am moving toward the origin. I may cross over the origin and then go away from the origin that way and then back toward the origin this way. Okay, and what we would do is over time, write time somewhere on your paper. Time is our input variable. Over time, we would map my position. So I start here. I start walking. When I start walking away from the origin. And I walk this direction for, let's say, 3 seconds. Then I turn around and I begin walking this way, right? And I walk this way at different speeds. I slow down a little bit. I speed up a little bit. Okay, and then I stop and I decide that I'm going to change directions. And can somebody let Chaz in? And I start walking this way. Let's say that I walk for about 20 seconds. And over that 20 seconds, I covered different ground, right? And what we would do is we would map, okay, I started here at 0 seconds. Then, after, so let's say here, I started at 12 feet to the right of the origin at time 0, right? Then I moved to, let's say by time 3, I was 14 feet to the right of the origin. Then I moved the other direction. And then at time, let's say at time 7, I was 9 feet this to the right of the origin. And let's say I sped up a little bit. And then at time 10, I was 2 feet from the origin. And then I turned around and I came back and I was at 5 feet at time, let's say I slowed down a good bit and it took me 10 more seconds to get over here to 5 feet. Okay? Are we okay so far? Yes. All right, so here's what I did. Basically what I did was, first I started here, right? Then I moved this direction. Then I changed direction and I moved this direction, right? Then I changed direction and I moved back this direction and ended here. Does that make sense? I know we're in sort of a lull here. We're definitely swimming in the deep end. We're good. Oh, you do remember this? Okay, from physics? Okay. All right. You might, yeah. Well, then you might be okay, but I need to warn you because we are about to get out of the pool and go get in the ocean.
drown first.
I hope. Well, that's why I want you to tell me if you're drowning, okay? All right. Ready? Here's what we're going to do, and I'm just going to kind of move this. I'm going to leave this up here so we can still see it. Watch what I'm going to do. Okay. You got to watch it, though. Austin, you with me? All right, watch. This is the x-axis. I am going to tilt or pivot the x-axis 90 degrees. Okay? I'm going to pivot the x-axis 90 degrees. Okay? So now, I'm going to miss you, Adrian. I hope I have somebody just like you in my class next year because you make me laugh. Your comedy is hilarious. And I know it's half serious to you, but it's 100% funny to me. Okay? And I'm not laughing at your misery because you're very smart and you usually wind up getting all of it, So you're going to make some people happy next year in school. So I hope you get professors that appreciate your humor. I really do. Okay. Yeah. Aw. You guys, well, I know it sounds lame, but you guys are all special. And I know that sounds lame, but it's the truth. Okay? Yeah. That's just another way of saying nobody is. You remember that from, what was it, The Incredibles? Yeah, everybody's special, dash. That's just another way of saying nobody is. Okay, so here's what I did. I turned the x-axis vertically, right? Okay, and now this is 0, and here's all our positive numbers. What is the x-axis mimicking here? What's it pretending to be? The y-axis. It's pretending to be the y-axis, right? So meaning all the numbers down here are what? These are all negative numbers, right? And basically, so instead of mapping the position right and left, we're mapping right and left motion up and down is what we're doing. Okay? So, and here's what happened. Well, let me get to this in just a second. So we know that we started out at 12 at time 0, right? Then we went to 14 feet right at time 3. Then we came back and we were at position 9 at time 7. Then we kept going, and at time 10 we were at position 2. Okay, and then slowly we turned around, and at time 20 we were at position 5. Right? So we did this. So all we did was we took this. We know we went this way, then this way, then this way, right? On a straight line. I went this way, then I went this way, then slowly I came back. Took me 10 seconds to get back to here, right? Only now, can you imagine looking over top of the x-axis? Can you see me walking? You're looking at the top of my head. And I'm walking this way. Then I'm walking this way. Then I slowly walk this way. It takes me 10 seconds to get to right here. Does that make sense? Okay? We're just taking a different view of it. It's still the x-axis. We're just viewing it from a different perspective, right? All right, now, this is the origin right here. So now, while that's happening, time is passing. Well, we can't really understand this very well simply by putting the times next to when I was at different places. There's an easier way to do that. I can make time its own dimension. I can, instead of this being a one-dimensional graph, just simply a number line, I can make it a two-dimensional graph by adding an axis and calling it time. Okay? So what I'm going to do is I'm going to add an axis here, and I'm going to call it time. Okay? So now watch what I can do. I now can spread out these points where I was standing. Even though I walked back, right and left along this x-axis, I can record where I was over time. Okay, so here's 10 seconds. Here's 20 seconds. Okay, here's about 3 seconds. Then I need 7 seconds, which is probably right about there. And that's about it, right? I think that's all of them. And then there's 0. There's where I was at the beginning. And if I do that, watch what happens. At time 0, right? This is time 0. This is the origin. At time 0, I was at 12 feet to the right. Correct? Then at time 3, what's that? No. Are you talking about those pictures? No. I'm just making a graph, a simple graph.
What?
I'm just making a graph. She was wondering if I was making one of those. That would be awesome. Oh, I wish I could do that. I'm not there yet. Give me a decade. Maybe I'll get there. All right, so look. At time 3, where was I? At 14 feet. So now I have the point 3 and 14. See, I'm turning it into a position graph, which can then, what's that?
Position is time graph.
Yes, which can then be turned into a position function, which we can then take the derivative of and have the velocity, which we can then take the derivative of and have the acceleration. Do you see that? Okay, so now, at time 7, I was at position 9. At time 10, I was at position 2, and I changed direction. And then at time 20, I have to get rid of our original x-axis.
Wait.
Because it's not, you know what, hang on a second, let me squeeze this in. Hang on, I got it. Here's 20. We'll condense it here. And at time 20, I'm at position 5. Now watch this. So what I did was, and now if I turn this into a smooth graph, I know I changed direction at 14, and I changed direction at time 2, or at time 10, position 2. And now watch what my position looks like. We can map my position over time with that graph. And so now we can approximately know everywhere I was at any particular time. And notice something. Okay, you want me to hold? No, we're not going to make a function out of this. We're just starting with we're strictly doing conceptual today. Strictly conceptual today. Okay? All I'm going to say is this is, because my position, by the way, this function, which is the x-axis, because we put t on the independent axis, this function is now the function x of t, position, x of t. X is a function of time. Position x as a function of time, right? Oh, Gabby, let me give you this before you take off. Read this between today and tomorrow. Just read through the questions. Okay? So look, but because the slope of the position graph is positive, what does that tell us? Because the slope of the position graph here is positive from time 0 to time 3, what does that tell us about?
You're moving in the right.
I'm moving in a rightward direction. And if it's a rightward direction, that tells me something about those things, those qualities we talked about. What does it tell us about? What's the derivative of position? Velocity. So if the slope of position is positive, my velocity was positive during that time. Right? And then what happened to my velocity? Negative velocity. Negative direction. And then what happened to my velocity? It went positive. See that? So everything that we have known as reading slope and derivative can now be said as slope and velocity. Okay? And that's pretty much where we're going. Okay? So here's what happened. Is all I did was move back and forth on a single axis. But while I was moving, imagine this. I'm standing here and all I'm doing is moving that way and that way. I need your brains to try and wrap around this. While I'm walking, there is a flat like plane of sorts, or a flat line that stretches this way, that's moving this way, almost like a well, it's hard to say. First it's time 0. Then it starts moving that direction. And as it moves that direction, I'm still only doing this and this. But because this line is moving that way, it's mapping my movement as time passes. There's 3 seconds right there. 3 seconds. There's 7 seconds right there. Meets up right here. Time is moving this way until I get over here. I'm at 10 seconds. Then here comes the 20 moving this way. As time passes, it's coming this way and drawing where I was at that particular time, resulting in a graph. I don't know if that makes sense. That's a mind bender right there.